Welcome back to another exciting chemistry lesson. In the previous lesson, we're talking about equilibrium constant, and that is represented by K. Then we also relate K to Q. Now Q is reaction quotient at any point in a chemical reaction, where K equal to Q is at equilibrium, okay? So K, it is at equilibrium, where Q, it is at any point in a chemical reaction. And of course, Q can equal to K, and that's what this lesson is about. So we already learned how to calculate K and Q using the same methods, okay? If we are giving a chemical reaction, when we write our equilibrium or Q, again, we are going to ignore pure solid or pure liquid. Now let's compare in terms of K and Q, and this is where it can be very challenging because you are going to compare K and Q to determine how is the reaction is going to achieve equilibrium again, or going to be at equilibrium. First of all, we know that when Q equal to K, the reaction is at equilibrium. Well, what does equilibrium represent? Well, the equal rate. In this case, you will see the equal rate of forward and reverse reaction. That is also there are no changes in the reactants or the product concentration or partial pressure over time. So that is at equilibrium. Now this is where it gets more challenging. Again, we already learned that when we write in Q and K, we're talking about the product and reactant. So try to summarize this in terms of this case. First of all, we have Q greater than K. Think about it. In order for Q to be greater than K, you would have more product, right? So there you go, currently more product. So what does that tell you? If you are having more product right now, okay, and you're not at equilibrium, in order to achieve equilibrium, what do you have to do? Well, first of all, we're talking about this is a reversible reaction. So therefore, reactant formation is favored. So that way, again, you have that equal rate of forward and reverse. See how that works? Okay. So product are consumed to make reactant because, again, when Q is greater than K, that tells you that you currently have more product. So therefore, you have to make more reactant to balance it out. Now, let's look at the other way around where, again, let me write this out. P over R, okay? When Q is less than K, well, what's that tell you? The only way that's less than K is the product values is less, okay? So they are going to change the wording in terms of reactant and product time. You have to visualize it. So currently we have less product or more reactant. You see how that works? So therefore, in order to achieve equilibrium, you would need to make more product. Therefore, the product formation is favored. And the reactant are consumed to make product. So again, take the time to digest the wording, how this can be twisted in different way. Now let's look at this in terms of a problem. You have a chemical reaction and it gives you the K. So this is again at equilibrium. When every time you see K, that's equilibrium. And here you have the molar concentration. We don't know if this is at equilibrium or not. So this is the molar concentration for each of the species up here, okay? Of course, this can be applied to partial pressure as well in terms of Kp or Qp. And what we do is this. We have to determine, now, first of all, it asks us, what is the reaction quotient? That's Q, right? Of the reaction. We know at equilibrium it will have this K, but what is the Q gonna be? So all we have to do is, again, we have to write our Q. Again, we ignore solid and liquid. In this case, all gases, okay? So let's write our Q. Q, again, is just the same way we write for equilibrium. We just ignore solid and liquid. There you go. See how I just write it out like this? And you don't see we have any of the superscript or the exponent because there are no coefficient. Over here, we have that. So we have x, y to the square because the coefficient right there. Next, we just substitute in the values. So we have x, okay? In this case is 0.2. Then y is equal to 1.2 divided by, what is xy? Xy is 2.0 to the second power. So we plug this into a calculator. 0.2 times 1.2 divided by 2.0 to the power 2. That turned out to be 0.06, okay? Now, that's equal to Q. Well, 0.06 is less than, so Q is what? Q is less than KC. What does that tell you? So let's go back here. Q is less than KC. Currently, we have less product, so the product formation is favored. So let's write down over here. Our Q is 0.06, and the reaction would produce more what? More product over time in order to achieve equilibriums again. See how that works? So take the time to write this out and plug it in. Be very careful about that part. Make sure to exclude any solid or liquid, okay? Now let's try another problem. Here we have this similar chemical reaction. I changed to K a little bit. So again, this works for Kp as well. And now we have the values and give us what is the reaction quotient. And of course, on your AP question, it's not going to give you something straightforward like this. It's going to give you in different format. But you should take the time to digest information. Q again is equal to, well, look at this. We have a solid, so we don't really care about that part. So we just have Y, okay, over XY. And here we don't have a coefficient, so we don't have anything on here. So all we have to do is just plug it in. So Y is what? Y is 2.0 divided by XY is 2.0 equal to 1. So here you go, our Q is equal to 1. Well, if Q is equal to 1 and our K is equal to 0.8, so Q is greater than K. So what does that tell you? You go back up here, okay? K is less than Q or Q is greater than K. What do we have? We have more product, so reactant formation is favored. So we are going to produce more reactant over time. And again, if you don't remember, write this in terms of product over reactant. The only way that's possible is that you have more product, okay, in order to have a larger value that's greater than K. So again, please take the time to write out the problem and start one step at a time. And if you have a question, take a picture of your work, put it in form, and we will do our best to support you from there. And we'll see you next time on another exciting chemistry lesson.